This conference will now be recorded.
Okay. Um, our speaker today is Yogan Senthil Kumar from TESOL. He's going to do a talk on known good die. And Mike, thanks as always for setting this up. It's all yours.
Thank you.
All right. So Mike and myself are discussing, and he told me about to give a presentation on known good die. So we did some internal discussion how we want to present. So this will be little high level. In certain places, we go little deeper. So the agenda I'm just showing here is the agenda that we're going to talk about. We'll go with is KGD a new thing? We'll talk about from the monolithic perspective versus heterogeneous integration, what the high level thoughts about it. Then we'll go into the significance of KGD from the chiplet perspective. And we will also talk about a little bit on the monitoring of the KGD as in when it goes into the heterogeneous package. We'll look into why it is significance. Then we'll talk about traceability in the event if a particular die in a package, for some reasons goes bad, and there is a requirement put up based on the ICs that are used in mission critical applications like maybe automotive or even for the matter of high performance computer. So there may be some requirement. So we'll talk about a little bit on the traceability of a KGD, and some of these very large integration, when we test as individual die versus as a package die, sometimes we may not be able to actually replicate the actual use case scenario. So we'll talk about the requirement from the ATE to leading to system level test, again a little bit in high level perspective. Then we'll go into how the test flow will look at. We will touch base on traditional versus now being some heterogeneous integration. How does the test flow will slightly change? Then, if time permits, we will talk about a little bit. This will be a little deeper. With some examples, I would say from our internal case studies. We'll talk about AT test and COT. Keeping chipless as a perspective. Then we'll do a quick summary. So this is the flow by which we'll be going for the next 50-60 minutes. Let's go into the first topic in the agenda. Here, basically in a monolithic IC package dies, dies are tested before being packed. Keeping the perspective that the package cost is expensive, so we want to make sure that the die we put in a package need to be tested. So this has been followed in many decades. The only areas is in the old technology where they know for sure because of the process maturity, they may do some blind assembly, but generally we do testing of the die, at least to certain extent. Then the after assembly we do a little bit detailed test, because eventually we need to test against the specification that is published, including to capture assembly defects. And also in the monolithic integration, the functional requirement of the package die do not change drastically from the die level, as in like the die you are tested in the wafer level is what is going to go into the package level. So the functionality doesn't vary that much. And if you talk about the DPPM control of the die, pretty much, it is that particular company's die, and whatever you kind of do, you are pretty much have a control over the DPPM that you could commit to your customers. But in the event that if you look at the known good die for the heterogeneous package, it would be like 2.5 or 3D package. It could include a third-party die. For example, it could be HBM. And individual die not necessarily define the full functionality of the packaged IC, because eventually when a company sells a product, it is the full packaged thing. Internally, they use a chiplet and other third-party dies. but that functionality is only partial. So these are all the various challenges that goes into when you look at from the chiplet perspective. And the assembly defects after package of a particular KGD may not be 100% directly detectable, as in like maybe there may be interconnects with other dies into the package, and hence the fault coverage that we want to think about need to be thought through from the in a various angle, including the chiplet level versus the fully packaged device. That includes the DFT approach that we would take in order to address this challenge. And individual die DPPM will come into picture. The reason being that though when a company sells us a fully packed device, the DPPM becomes additive of the individual KGD that we put into the package. If there are 12 ones, then each one individual dies DPPM comes into picture. So there is a challenge when the end customer requests for certain DPPM number, then these challenges comes into picture in order to address that. So this is the little bit of intro I want to give. Then I would go into the next topic. What is the significance of KGD from the chiplet perspective? Here, if you look at, when we put a chiplet into a package, basically the die-to-die interconnect within the package is going to be in terms of few millimeters.
Good
In other
morning,
words,
ladies.
sorry, was there a question to me?
Oh, never mind. Hey,
Okay.
would you go on? Keep going. I'm sorry about that.
Sure. So while we help to optimize the drive strength and then hence to optimize the power consumption, in other words, if the chiplet is going to only talk to the next chiplet within the package, the distances in terms of millimeter, then the IOs can be optimized for space and performance and the power consumption. But what happens is that die need to be tested again in before it goes. So it poses a challenge from the AT perspective. That means 80 channels are usually in terms of maybe 6 to 7 inch away from the die. So how do you strategize to ensure that the die you're testing, you still able to test properly, keeping this challenge in mind? If you do have a high speed interface, definitely loopback test is very much applicable even for KGD. The only thing the strategy need to be looked upon is internal loopback or external loopback. Accordingly, the decaps which will connect the TX and RX differential pair, all this comes in picture, and eventually it's lost when you bring it out to the trace, which may not be exactly same as you replicate into the package. So some thoughts need to be put on that. And the test time of an individual die on a AT would be in seconds, which is very much applicable even for that matter, even the chiplet perspective. But within the seconds, we are taking a pass and fail decision, not exactly testing the way the end application requirement. So there are some challenges, and this KGD is going to go into a bigger function later to be tested. And of course, all the pins that we would have tested from the die, when it goes into the package level, all may not be available. Of course, it will limit the performance if you want to bring it, and also the pin count increase, and eventually the package size and the cost will go high, so it's not possible. And again, it reiterates that we need to look at methodologies from the DFT perspective and the performance perspective, and come out with a test strategy when we come to heterogeneous integration. Also, the reality of SI, here when I say SI, it includes power integrity and signal integrity simulations that we might do on a substrate design versus what actually manufactured cannot be assumed. The reason being that the package cost and so much die we are going to put in, and if there is an issue, we are not able to meet the performance, it is very critical. In other words, what we simulate in a package substrate need to be also verified whether manufactured substrate really behaves the same. In other words, a tight manufacturing tolerance and line width space and other aspects are critical when you choose a substrate manufacturer. And the substrate manufacturer, once it is manufactured, they will probably do a netlist kind of open and short for the netlist. But it is also critical because there is going to be very high speed interconnects between one die to another. And if there is if not for all the substrates, but in a sampled basis, if we could able to test those substrate for the actual performance, it could be like, insertion loss, reflection, or to some extent, eye opening. uh, Bit error rate may not be required, at least some eye opening. At a sample basis, if it could be done, it'll be great. If that will impact on some of the cost on substrate being damaged or something, then we could choose a critical signal for worst and best case within that package and replicate as a small coupon like we do in the PCB. Some sort of stuff can be explored for the package side, and you only those test those coupons in order to just to make sure that the substrate manufactured is really behaving the will reflect the volume of the substrate manufactured. So this could be one area that we need to look at from the chiplet perspective. And of course, as we test the chiplet, then it goes to the substrate, and eventually we do it. And there is a way of a layer of tolerance comes into place. This could be that tester instruments tolerance. We are talking about the load board. From load board to load board, there should be variation because of the manufacturing aspect or the components. If you would have used a relay or some op amp, all has got tolerance. And eventually, when we say that this is a known good die chiplet, these tolerance need to be kept in mind so that when it goes to the heterogeneous package, it doesn't influence a pass becoming a marginal fail or things like that. So in this case, we have a lower data sheet limit and the upper data sheet limit. The sigma need to be come into place. Is it 3 sigma is good enough? From the lower limit, you push it little up. From the upper data sheet limit, you push it little inside. So a pass region need to be thought in keeping this in mind. Of course, this need to be compromised between the performance, yield loss versus the end application requirement cost perspective, and need to be kind of re-liquid into it to arrive to a KGD from the chiplet perspective. With this, I'll go to the next aspect, which means imagine we put all these chiplet into a bigger package and we do test. And for example, due to margins or some issues, or it could be the manufacturing issue happened in the substrate, for some issues. What happens if, first of all, we need to be able to test. So assuming that we put some DFT structure to test from each chiplet. So I'm quoting some example from like a kind of SSN kind of architecture or 1149.10 from the DFT architecture. In this case, we are saying that there is a circuit under test. Um, um, we can consider this as 3 chiplets, for example, and we did a DFT architecture. If there are say multiples, we should think the DFT architecture also in sub-block approach in a way that, for example, one of these dies goes bad. How the DFT architecture still permits to test the excluding this particular failure and able to communicate to the other chiplets to make sure it tests. So if there is a way to do that, then the device manufacturer can look at, how can I sell it as a next level, lower grade device. Then definitely you don't want to throw if there is one chiplet. That is one aspect. The second aspect is how can I bring in redundancy? It could be a small memory that it was failing. If there are redundancy available to repair it and replace it, so that we can recover from the failure and still sell as a very good fully integrated chip. So these also comes in mind, comes in place. In other words, the chiplet, if it's bought from the third party vendor, if it provides such kind of feature as a part of DFT built in, then it helps to implement as a bigger system level, because the chiplets could be from the third party vendor in some cases. That's what I'm trying to convey here. With this, I'll go to the next agenda, which is the known good die monitoring. When we put in 3D or the 2.5D package, there are many things in. Of course, we do a lot of simulation, for thermal and power rail performance and so on and so forth. But still, it is a simulation. These are all going to be in a heavy compute area. The workload that you put on one of the core or one chiplet versus other need to be monitored in a way that which you can push, you need to bring it down. In other words, there is a monitoring required within the package device. And also look at the thermal perspective also. If you put everything, what you simulated versus in the real field also may be required. And this will help also. So we can look at, PVT monitoring, like, process monitor. It could be like a, ring oscillator or something. And the power rail voltage monitoring, if, for example, the core is operating in 0.8 volt, what is the margin you want to give? And the current workload that the chiplet is running has gone very low to the threshold, or is it upper to the threshold? If it's still lower through the threshold, and you can push, further, compute power into it, so that you can do a dynamic kind of, performance monitoring based on monitoring this. So it does help in that aspect also. So with this, the process monitoring will help with the behavioral understanding from the wafer level, so that a marginal pass die, do you want to consider or not? You could look at some of these behavioral from the process monitor. Whereas in the power rail voltage monitoring, based on how it is performing, the compute performance can be optimized. And also, if it goes, lower or upper threshold of the rail which you're supposed to operate, yeah, kind of, alarm interrupt kind of mechanism can be built in, so that the device, or an operation can be taken place in a sense like, should we lower down the performance compute required in that device, or should we bring to a safe state? Those kind of analysis can be done from the firmware level also. And it could be also be considered as a part of power on self test. Whenever you turn on, if it's internal monitoring is there, it could help us to give the health of the system in the beginning itself. Similarly, that is applicable to, temperature monitoring. There is a workload running, but the device temperature has not increased. You could push even further, of course, monitoring the voltage rail also. In their way, the performance can be monitored, and this could be also saving for the power, in terms of considering, if it is there in a bigger scale integration for data analytics and things like that. Are, it can be also again considered for power on self test, and also, as a part of mission mode test also we can look at. That means mission mode test in a sense that while the device is working, we could still go and read this, and, take some decision based on monitoring the performance of these die level, and also in the package level. The other aspect is the structural monitoring. In other words, every device has got an aging property due to, various effects, like, NBTA or hot carrier injection, or the time dependent dielectric breakdown. And these are all going to be in a very mission critical applications. There are design vendors or the models available for each technology node. So if there is a aging model, it is definitely we need to run the aging model to find out how does, for example, a propagation delay differs from the age, so that, the setup time, hold time, how does it impact, and this could trigger a failure eventually down the year. And with having said about this, there are now talks, because of this complexity, path margin monitoring come into place. It is a, simple way to explain this is, for example, you have a flip-flop, you have a D and Q, you go and monitor the transition with a little higher resolution. So you strobe it in a little faster. So you get a signature, for example, D, there are little highs and more lows. For example, in the output, you have more highs and less lows. This could be a golden signature can be put in. and over a period of 1 year later, 2 year later, if there is a differ in the signature, some analytics can be understood, and we could tell the path the device is going to age or not. And of course, this is only a simulation. We could do hast, to find out accelerate it, but the device is actually naturally aging versus accelerate aging. There will be definitely difference. So such path margin monitoring would be of help for a very, very, very high integration, like using chiplet. So the EDA vendors now started providing tools for this to implement right from the design to production ramp and volume. They call it as Silicon Life Management as a package. So this can be explored for such a kind of integration. And right now there is no standard defined. I kind of looked into it. So industry has to come out, to come out with the standard of how this can be implemented. In that way, it becomes a proper part of IEEE or some kind of standard we could implement. With this, I'll go to the next topic, which we call it as a traceability of known good device. So what happens, a heterogeneous packaged IC fails in the field. So if you look at the bathtub curve, because of such integration, I'm sure these kind of devices going to be put in a very performance requirement kind of places like data centers, or it could be automotive, where a high fast graphics compute is required to determine the certain hazardous in front of the vehicle and things like that. Anyway, so here any bathtub curve we have infant and normal life and end of life. But what happens is, if there is a failure for assuming this kind of package device is going to a very critical application, the traceability importance is too high if there is a failure in the infant area versus the normal life and end of life. I'm not saying that there is no need on the end of life area. It is still required because the industry requirement is like that. But the pressure on finding the root cause during if there is a failure in the infant mortality period is too high. So what will be required? If you look at any package, because of this heterogeneous integration, there may be a link to a particular wafer ID, this particular one of these chiplet came from, and this is applicable to each and type of devices that would be memory, logic, things like that. So, and we have a die ID, then there is assembly data and test data goes behind it. So these need to be analyzed to come out with the root cause where the probable issue could be. So OSATs provide a unit level traceability as a kind of a 2D barcode which could be printed in a device. In our case, if it is a chiplet, maybe they can do a barcode as a back of the die. But again, once it is packaged into a bigger package, that may not be readily available. Still, maybe the guy who did the assembly, guy in a sense like the OSAT who do the assembly, could decipher and take it, but that is going to take maybe 2 days or 3 days to kind of figure it out. And that for the application requirement, that time lag just to find out what is who did what may not be acceptable. And for example, and again, these data need to be kept for 5 years. In the case of automotive, you may need traceability up to 15 years. Keeping that in mind, also the application requirement, for example, automotive grade ICs which are in ADAS 4 level or 5 level, and probably for high performance ICs, these may not be acceptable because of the requirement. Yeah. So what happens is, there may be a need at this point of time to look at the traceability can be embedded into a small memory if the area can permit to provide this. So some of these IDs comes as a 2D package, can be put into some kind of flash memory where it can be read when it is required. And the reading, you don't need a very high speed stuff. Even a SPI bus, if it can put those information, And thereby, if there is any failure or abnormalities found, these data can be pulled into a standard established protocol, like for example SPI, and this can be thrown, which means all the data analytics behind the chip need to be written, and this can be readily available if there is a malfunction or something detected, and the traceability of data, at least to the first level, everything will be available immediately. So these need to be also thought through as a part of a traceability for known good die. And semi traceability standard committee has got some standard for semi 223. I'm not gone through it, but we need to look at if this really pushes to the way the industry needs. If not, that may require updation or some other kind of standard need to be developed and adapted. So this is what I thought I'll cover on the traceability of KGD. Then I'll go to the next topic, which is the actual use case leading to system level test. In this case, as I mentioned earlier, we test individual dice, and through AT environment, we put them into a heterogeneous package, and we do some test, and we test it and tell it is good or bad. But most of the times, the AT's way of looking at is, you do some structural tests, we do some functional, we do some memory based. These are all like a silos, like individually we tell the blocks, if all the blocks are passing, we tell that the device is pass. Whereas this may not be uh, able to capture all the field errors. This is something probably very matured for processor companies like big companies like Intel and AMD. But now that chiplet based integration coming in, the system level test is very much required. The reason being that it has the ability to test a chip or a multiple chip in a package in the context of how ultimately it will be used. And definitely, you do a AT level test in few seconds, or probably 10-20 seconds, versus a system level test which will run in minutes. The thermal hotspot produced will be different, and definitely there is a gap in, like the type of errors that system level test would capture will be of course the AT test does a job, but it will system level test able to cover the other areas which the AT test may not be able to capture. So as I mentioned, just now, in AT test, we really look at the structural aspect and test all these blocks. And if it passes, we tell the device is passing. Whereas, for the ICs, like, complex ones in terms of high performance compute, um, we need to look at how it will be applicable in the real field. So it will use such as the support ICs like PMIC, external memory, display drivers, and so on and so forth. And usually it runs on a customer specific firmware, which is not a part of AT test. So it is important to mention that also that the external component and ICs may not come from the same manufacturer. For example, you have a chip from AMD or Intel, the other chips will come from Hynix or Samsung and so on and so forth. So there is another variability that system level test will help to address the issues that may not be captured by AT. And also, testing for a customer specific use case becoming a key need, for mission critical applications. For example, it could be automotive or data centers. People talk about silent data corruption, which may not be captured at 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 all. System level test could capture. There is no statistic at this point of time. The silent data corruption could be captured or not, but eventually such thing will help to improve the DPPM to a next level just than do AT test. So what is the facts when compared to AT test times? So definitely the system level test could run into several minutes, and the number of parallel devices tested in AT is limited because you have a number of channels as a resource in the ATE, and of course the limitation could come from the power supply also, and you do like 4 to 8 device test as a maximum. Whereas SLT, the test times could be in minutes. So definitely parallelism is one of the key thing. So here you're trying to test in hundreds of devices. Of course, the it doesn't use any of the ATE resources, but you need a specialized handler for that, and that will call for an additional capex. And
Hey, maybe a quick question if you don't mind.
Absolutely, yeah.
You may have addressed that, sorry, but I joined a little bit late. So system level test, is that like too late? Because if you fail, you're failing the whole system. Is there anything can be done to reflect some of those tests early, so you could like remove the offending device rather than the whole system?
Your voice is feeble. If I understand
Oh,
right, are you saying that is
I'm
this?
saying, how would the system level test help you? You've already assembled everything, so if you fail, you're gonna throw away the whole system.
Well, yeah, I'll show you an example. I will answer your question. The system level test can be still performed, not assembled one, in a socketed manner. We did some work. You still, that means you remain, all the hardware is there, just the device is only inserted and taken out. So if the device is bad, you basically, throw it, but not the whole system. So this system level test is little different from the kind of system level bring up as a full board. Can I go to the next slide? Probably see whether that answers your question.
Jürgen, Mike here.
Yeah.
Just another quick comment as well. That's the reason we do known good die flow, so that you, by the time you get to system level test, you're fairly confident in all the die and all the packaging that's gone on in advance. And so known good die flow reduces the risk of a system level test failure.
So you expect very, very little failure at the system level?
Well, it depends how good your testing was on the devices in the known good die flow. But and also remember, system, as Jürgen mentioned, system level test is testing something which maybe we didn't test in ATE. So there is some risks there as well. But one of the things you can do as well, if you get a failure at system level test, once you've debugged it, you can push back tests into the known good die flow to reduce the risk that you'll get that failure again. So
yeah, that's what I was probing basically, is like, how can you do that?
But, you could do that. You could, but by doing a failure analysis on that system level test, and people do this, and a lot of people do this because of the time it takes for system level test. They do it to reduce test time mainly, because they would much further push system level tests into an ATE, which they can do a lot more quickly. So there's that level of analysis as well as improving yield. It should reduce system level test time. But anyway, I'll let Jürgen carry on. Sorry, Jürgen, carry on, please.
Yeah, sure. Yeah, thanks, Mike. Yeah. So system level also can be looked upon as a strategy, as a safe launch for the initial run, just to make sure that we cover as much as false before we do. So the picture here shows basically one of the solution we have done. This is not for bigger volume; it is more for kind of NPA launch. We did it for one of a medium complex processor with which has got about quad ARM core. So if you look at this, the hardware, you have a socket. Of course, when you put into the handler, the socket lid will be open. The device will be put in center here. This is the backside of the hardware where all the interfaces are coming in, and this is like 1 feet by slightly less than 1 feet kind of size. And solution we have developed, and this is the board we goes in, and there is a computer which sequences the flow of running the test, and this could be docked to any existing AT kind of handler, and you could run. In this case, you can probably do single site or dual site kind of test, but the test time will be higher. But certainly this will help to kind of initially to launch yeah, in a safe mode any new product. And one thing you need to note is to enable yeah, kind of system level test, a typical test engineer with the AT experience may not have the knowledge to write the use case on some of the operating systems like Linux and Android. So hence a collaborative approach of embedded expertise and the software expertise is required to put some of these devices into kind of production. So with this summary, I will just put some flow, how, for a chiplet based IC, how the flow could be. Definitely, if there are three types of chiplet goes into a package, they need to be tested at the as a bumped die, and these can need to be tested to the maximum parallelism as possible. Of course, in this case, if you want to look at the key areas, so you could consider a low cost ATE by doing a proper DFT strategy. So you do the scan and other vectors. And if there for the other high speed lines, if a DFT structure can be put in where, there is a PRBS generator, you pump in the vectors, and through the TX and RX pair, you loop it and bring it back as a parallel and read the fail signature to kind of. So there is a possibility to put from this level into a little low cost ATE, and the parallelism we can look at depending upon the die pin count, maybe up to 8 kind of, device to be tested in parallel. In the package level, the complexity increases, and as I mentioned earlier, the package substrate also influences on the performance. So yeah, a solution we develop is a little complex. A high-end AT would be required, and in this case, because of the pin count increase and the resource available, the parallelism at which you could test, it could be 4 to 8, or sometimes it could be a couple of, only 2 sites you can test in parallel. And as for the site, the reasons that we talked about, SLT could maybe required definitely as a after you do a AT test, and a single site AT kind of SLT kind of environment, you could be used with the existing handler for the kind of new product as a safe launch. But when you go to volume, you kind of need a high parallel SLT solution to run on a proper SLT handler, and we ship to the customer. And there are customers, we have seen people, even after SLT, they want to do some confidence building. They do some basic test, one more kind of thing in a AT, in maybe a low spec AT, do some continuity and some kind of shots, so that, just they want to ensure that SLT, after finishing everything, it is not spoiled or, did some basic, issues. So they do some more test if required. So you need to look at this point of time, yeah, chiplet based kind of solution, definitely test cost is a key aspect of it, versus a monolithic kind of integration. But certainly if yeah, for a given process node, if your reticle size is almost like 70 to 80%, then chiplet based is the right approach for scalability future perspective. Of course, if it is, your reticle size of your mask is much lesser, then you could still consider as a monolithic. But when you go to chiplet, test is a huge area to determine the ultimate yield package level and its performance. So there is a various aspect comes into picture is what trying to cover in this flow. The next slide, I will go a little deeper, but we can take our time, to go deeper or quick, depending upon. I think we have another 10-15 minutes. Let me cover this a little bit. I have taken this from our use case, been real application data, so I'll show some stuff. So every chiplet considered for heterogeneous integration need to be tested. So it's going to add cost. For example, if a chiplet is say 140 micron pitch C4 bumped die, the picture shows is one of the 93K load board where we have a vertical probe card, and this is a very complex board, and definitely you want to achieve as many die touchdown as possible to bring down the cost of test. So of course, this will be limited by the number of channels and the power supplies capability to power up as many dies as possible. But this is one area you need to be thoroughly looking at to bring down the effective cost of test. In this case, also the PCB layer, when you go to multiple die, it can go up to 40 layers. and achieving a manufacturable aspect ratio for the given PCB thickness, because the AT vendor recommends certain PCB thickness, for example, approximately 4 mm, is a challenge, because that is going to impact on the yield and the reliability. So a compromise, the balance of fab yield versus NRE cost need to be kind of arrived, keeping things in mind. Also, wafer level test generally covers a DC parametric, scan test and structural test. In package level, there will be a more, functional aspect will be tested. But if there is a possibility, the things I cited, the drive strength of the chiplet will be little less. How do you tackle it so that the dice can be tested at the die level or the chiplet level? Also requires a key aspect that need to be considered as a part of hardware design. A typical hardware design pricing, including the MLC with vertical probe card, easily can exceed 100K. So imagine if there are three different types of chiplet, and it is going to increase. And when the chiplet is manufactured at higher volumes, each type need to be replicated for 4 or 5 boards, and hence the cost of test is a key thing that need to be analyzed from various angles, as cited here. Um, Also, if you look at the parallel test of the packaged could be limitation, not just come from the digital channels which drives those signals. It could be come from the power supply itself, because some of the power consumption of the device could go up to higher wattage in terms of 100 watts kind of range or even more. And the high-speed line interface budget as a package level also could limit. So tight budget tolerance and the length matching all comes into picture. And you need to look at, and we do put relays and components which will eventually have its own tolerance. And what happens if one relay goes bad? How do we detect it? It's also going to be a key thing. So we need to look at a way how do we diagnostics such complex hardware, and how to create some calibration offsets for the onboard components, so that when we test, we really measure the device performance by nullifying all these effects. PA and SI simulation are very crucial for avoiding very expensive hardware design respins. I can quote some examples here. Before that, let me talk about the one thing, the loopback thing. For example, we may put a capacitive coupled loopback. In the event that you want to do also some DC parametric, we can look at yeah, inductor kind of thing. So it will kind of behave like a bias in the RF side world. So you could do some DC measurement and bring it and test. In the event that the drivers of the DUT is very weak, now there are MEMS based loopback, which is very, very small. I think AD and few other companies, Korean companies, are making as a differential loopback, just capacitor coupling or with the inductance, so that the transmission line property of the device are kept in a very good intact. So we could look at MEMS based loopback kind of implemented in the load board for better performance. PA and SI simulation is very critical. You could do, and if you look at in this picture, the blue shares where there is not much of drop, the red is where the drop is. Improving, that means your PCB design should not limit the measuring aspect of the device performance. So in this case, the stack up layer planning is very important. For example, the high ounce copper in the PCB trays may be exceeding more than 1 ounce could be considered. Even if that is not enough, you could look at sandwiching the similar shape in the adjacent layer and stretching with the vias, so that the DC drop can be kept minimal, so that we don't throw device because of the load position issues. Plane impedance, one is the DC drop, the other one is the plane impedance. We need to look at the critical switching frequency based on the PLL or the other aspects, and we need to optimize the plane impedance. For that, you need to look at the write up of caps used with the low ESR, and in the combinations of small value with the bigger value need to be arrived to kind of arrive those impedance. Those are critical in just to ensure that the hardware is works in the very first and avoiding respins. This is one example. We we found through simulation there was a mistake. This is the topology where, from the one of the MIPI driver, it goes through certain relays and goes into the receiver. The relay had a ground plane across its footprint in the adjacent layer that became too capacitive. And when we did it's not for all the relays. The engineer had a genuine way to implement. Somehow, when he did the copper flooding, he forget to remove the copper thing. And in one of the relay, there was an issue where, through signal integrity, we could found that, the eye opening is too bad. Then we found that and removed that, the copper on the beneath the relay, with the ground layer, and the kind of thing improved better. So, in other words, the reason why I'm saying is PA and SA is so critical. We shouldn't skip this, and we should thoroughly check all the, not just sample that one path, but all the critical path need to be evaluated. That will become a more workload for the simulation activity, and hence the cost of designing the hardware will be high too. And similarly, for the for PCA, those kind of things, you need to look at the actual model. So whatever the capacitor views or the MEMS aspect you put in, get those model file and built into and simulate it properly, just to make sure that at the simulation level it is taken care. And when we fab, you need to really look at the fab which has got tighter tolerance in terms of manufacturing, so that what you simulated will kind of go close to what in the real performance. Correlation is another aspect. So correlation happens in bench measurement to AT measurement, and for a particular device, you will not do one board, you will do multiple board. So board to board correlation will come into place. Then within the board, there are, if you say, in this case, you are talking about, 12 sites, every site is matching with each other or not. So site to site correlation is important. Then when the volume picks up, you will not just run in one ATE, but you will do as a kind of 3 or 4 ATEs. So ATE to ATE correlation comes into place. And over a period of time, if you do a test time reduction, again you need to enable ATE to ATE correlation. If required, all the whole yard you need to do one more time. So these are all things will become very critical when it comes to chiplet based integration. And this I already talked about. So God banding, considering all these are very critical, so that eventually the end product behaves better. 3 sigma is a standard, but should we go a little higher considering all these things? All the things we need to look at case by case basis. So this is what the presentation is. I will do a quick summary. The overall package DPPM becomes additive of individual KGD. So all the points that I talked about becomes very critical, so that to define the overall product DPPM level. And having the chiplet IO is optimized for the required dry strength between die to die interconnect. When you want to test it from the AT perspective, loop back test and other aspect need to be looked at it in many angles, so that you truly test and test the performance of that particular IC. DFT architecture cannot be ignored, both from the chiplet level and the heterogeneous level, so with keeping some redundancy to achieve the yield. And in-chip monitoring and die level traceability is also a requirement, so that eventually when the device has issues or fails, how do you trace back is a key thing. And God banding, the requirement with the considering all the thing is also a key thing. And at last, I would like the system level test, running an actual use case test will help you to, at least in the initial period, is going to greatly help to capture some of the errors that eventually the field will look at. So that's pretty much the summary and the presentation I have. If there are any questions, I can.
Maybe a quick one along the first question. The system level test, are you saying you're actually socketing the die rather than assembling and testing, but you're actually socketing every chiplet basically in a system configuration and then testing?
Yeah, so generally the system level test is done on a fully packaged level, but what I'm pointing is, this need to be looked at. If the chiplet itself to be tested from the system level perspective, that is one aspect to look at it. At least when you sell as a packaged device to the end customer, the fully packaged, the 2.5D or 3D packaged device definitely need to be considered for system level test. And again, that will be definitely a socketed test. Yeah.
Yeah, no, that I get it. But do you have an intermediate stage, you're saying, where you're actually socketing the die, and testing them in
Yeah.
system configuration? You have that step as well?
See, chiplet is kind of coming as a new thing. Testing the chiplet from the system level perspective is I'm not commonly heard, but that is something as you said, we should be looked upon too.
Okay. Okay.
So you're not do. How does this work for like advanced packaging, where you may not be able to do, you know, some of this testing uh, for known good die and things like that? So certainly at speed, right? So how do you see any issues with that?
Yeah, so as I cited out, the AT will have certainly a limitation for a fully packaged level. What right now what we do is the customer we have seen is we take our real application board that this product will be eventually put into their customer, and we need to write the use case scenarios like stress test, or for example taking a data, and for example if it's a gaming application, take the user input, do a graphic compute, and throw out the data in terms of videos and other things, and see the as a system the temperature and other things are well within the control. So that requires a kind of software and embedded teams expertise. So the system guys will help to write those use cases, then the test engineer will kind of sequence it to kind of do it. And sometimes the actual firmware that eventually their end customer will using can be ported into the system level test. In that way, for example, if Audi is testing they are using the device in certain way, that is their firmware, we can bring that and put in and run those real use case tests, so that for that customer, for their application requirement, we are able to test it to get a extra confidence that the device, that the package device that will ship will eventually will have less returns, or the aim is to have zero returns. So the board also can be configured. For example, eventually this will be used with the Hynix memory or Samsung memory. So you can have a flavor of boards with a different memory, and the device can be tested accordingly. Are you able to hear me?
Yeah. Is that Yogan? Yeah.
It was quiet, so I thought I'm lost the line or not.
I'm just aware of the time, Yogan. We've got 4 minutes left. I think Bappy's left as well, so I'm not quite sure who's now managing the meeting.
Okay, sure.
Do we have any more questions?
Can I ask a question?
Yeah, sure.
Hey, nice, great presentation. One question is, what is your opinion on? I know you have a bullet for DFT architecture in the summary, but what is your overall advice or suggestion on how DFT should be handled, especially from architectural perspective when the chiplet definition is started, and you know what kind of custom chiplet or ready-made chiplets are going on a package?
Yeah, so we had some discussion internally in some requirement. So looks like SSN kind of strategy is what is going to help. But as a full integrator, the chiplet will come from different vendor. So what kind of strategies put in the chiplet is something need to be understood. But if it is just an IP that you are going to integrate and do it, then you could go and change the DFT architecture to your requirement. If it is comes as a chiplet, right now we are also discussing how this is going to uh, uh, proceed, looking at the challenges behind and what type of redundancy you need to put, considering the area that you could allocate, but budget you could allocate. So we are in this discussion, but right now we are looking at SSN as a means of saving or giving a torchlight to go further into the DFT perspective. That's what we are looking at. And recently I was in ITC, they talked about SSN could be the way that we could adapt to such high integration. And there are some EDA tool vendors. I'm not a DFT expert, but the EDA vendor tools have started addressing multi die integration, keeping SSN as a way. So that is what I think at this moment the chiplet industry should adapt. Not sure answered your question 100%, but
Yeah,
this
yeah. That's yeah. That answered my question. But I didn't understand when you say redundancy. What is redundancy in the uh, aspect of in the context of DFT? What is
well,
that?
for example, if you do some memory based, there are some from the chiplet perspective, everything functions well. But if you put into the bigger package and you feel that there is some memory failure for various reasons,
Oh, okay, okay.
so you still need to have a ability to go inside and repair and bring back the spare memory lines to kind of address and data lines to kind of so that you don't waste the thing. So it is not just for testing the die alone. There should be still spare available after it is integrated through a 3D package so that it is available for you to still correct to some extent.
Thank you.
I'm just aware we're out of time. So, I think who's I think DJ, are you the organizer now? Because I guess we could finish here. If there's no more questions, DJ, I suggest we finish because Bappy's no longer on the call. Okay. Any more questions?
Yeah, can everyone hear me?
Yeah. We can
Yeah,
now, yeah.
just one point I wanted to make for everyone. Uh, Everybody's slides for OCP Global Summit are due today. So please do the needful and take care of submitting a draft of your slide. They don't need to be in the final form. They can be in a very, very rough form, but at least it gets into the system. So with that, I think we can close the call. Thank you, everyone.
Thanks, Jürgen, as well. Thank you.
Thank you.
Cheers.
Thank you, guys. Have a good day. Bye.